Okay, so I wanted to talk about some work that's been done as part of actual proposed sewage systems to look at different kinds of materials and cementitious materials to improve MICC resistance. And they've been done on a couple of different projects. Just because I gather we're over time here anyway, but the basic problem is, as has been generally alluded to, is that Portland cement-based concrete has a bit of a problem with acidic environments, and MICC is such an acidic environment. And while we talk about sewers, this kind of environment also occurs in other kinds of structures. And it's a very important point to remember that even extremely high quality Portland cement-based systems can still have quite a lot of trouble in these kinds of environments because of the basic chemistry. Other speakers have talked about the complexity of MICC, but I would add to say that it is, while the focus is on sulfuric acid, it is an incredibly complex chain of chemical and biological reactions and a lot of different little animals trying to cause trouble. And I will be referring to some exposure work that's been done. Some has been done at Kiwa, mainly at the University of Queensland, and there's some relating to a German standard as well. This has been discussed already, go through that. One thing that hasn't been mentioned as much is the impact of moisture conditions is a very important part of the equation. And so this was some field studies that were done in Australia as part of the SCORE project, which showed the relationship between relative humidity and the rates of corrosion that they were measuring in different areas. And yeah, this is some rates of corrosion in different manholes on a facility in Sydney. And just highlighting one of the points that you get very highly variable rates of corrosion can occur. And that's one of the reasons why I think that having more microbially induced corrosion resistant concrete to just improve these deterioration parameters rather than very expensive linings through the whole system is probably a very economic way to go. This has been discussed. Basically, Jason went through the kinds of tests that are available. What I'll be looking at is just a couple of examples where different kinds of binder systems were used for different tests. The German standard, this is called the test of resistant to biogenic sulfuric acid, but unlike the current proposal for a benchtop test in ASTM, this is just sulfuric acid. The procedure, so this is an immersion test relatively similar to the C267 type of test, but they did have guidelines for this. So one of the utilities was interested in using this test because it was a formalized international standard, and it actually gave performance parameters for different kinds of levels of resistance, exposure to pH of 0 and pH of 1 for 14 and 17 days respectively. The procedure involves these are all in centimeters. So this is essentially 4 centimeters. So, you know, sort of 1.75 inches sort of style by 1.75 inches cross section. And then doing a compressive strength of across this little cube that is developed here. So you can imagine it's quite a complicated test, and with such small specimen sizes, you have to be very accurate with doing your compressive strength work. But visually, the most interesting way of looking at this particular study, which was done at the University of Sydney, is this B1 at the top of this slide. So it's looking at different levels of of acid, so pH 0, pH 1, and looking at it being brushed off and looking at the cross section. This was about an 80 MPa level, so of concrete, so say 6,000-7,000 psi concrete, or maybe more than that. No, maybe about 10,000 psi concrete with fly ash in it and a bit of silica fume, and it got smashed in this environment. And this particular concrete was with an antimicrobial. This is ARCB, proving the point that's been raised earlier that using antimicrobials is not going to be able to help against this sort of straight acid attack. K, this is a calcium aluminate-based cement, and so these are materials that are performing well, and this is a geopolymer concrete, and this is an ambient cure slag fly ash system. And so it was really sort of chalk and cheese between the exposure of Portland cement-based systems versus the calcium aluminate and geopolymer in that particular test procedure, but it certainly has its limitations. This is the Kiwa facility, and so they tap into real live sewers in Hamburg, I believe. Berlin. And so that's where they're getting their effluent. They then have a residence area for sort of generating real live exposure conditions. And they have developed over time these different, this set of performance parameters to assess the performance of concrete when it is exposed to quite a severe MICC environment, some of which are quite intriguing, right? There's even a freeze-thaw resistance issue to do with microcracking. Other things, they do total porosity, but these are down at very low numbers compared to what were just presented earlier. Even migration so there's a range of different parameters which are looking basically at the penetrability, but there is also a deterioration rate. And generally speaking, there was a test. One of the projects had this blend of calcium aluminate cement and slag, as well as a small amount of Portland cement, and performed extremely well under those circumstances. So that may well be something that's of very significant interest in the future with regard to this area, because basically calcium aluminate cements have been in this area for 70 years or more, but they're expensive and a bit complicated, but diluting them with slag seems to be quite an efficient way of improving a number of properties, including reducing conversion, as well as reducing temperature rise, for example, and cost. So that's something of some interest. The Advanced Water Management Centre up in Queensland, they have a biogenic corrosion chamber, and so they test a number of parameters, but the primary interest really is in doing the photogrammetry and the corrosion rate. So that's the number that comes out. But they do also look at sulfide uptake and surface pH over time. So you can. One of the questions was asked about the influence of different kinds of cementitious systems on stage 1 and 2. So looking at that initial pH drop can help in that regard. And indeed, calcium aluminate cement is basically focusing on retaining, because of its buffer potential, it's effectively elevating the pH and preventing the pH from dropping too much below 3 or 4. So this was part of a project over in New Zealand. Again, this quite high quality OPC system with other cementitious materials in, the microbial, the calcium aluminate, and a proprietary geopolymer. And so there is the two lines here. So their particular chamber looks at having panels of the concrete in the gaseous phase and partially submerged, and the partially submerged in much more aggressive condition, and getting these pretty high numbers. Again, it's pretty high quality reference concrete, improved to some extent with cementitious materials in that system. Microbials helped in this regard, and calcium aluminate and geopolymer performed well. This is the kind of samples and specimens that they use in that procedure. And in another project, this is up in Asia, where they nominated that there was a requirement for a 1-year exposure trial at 30 degrees, because it was in Asia, and with 100 parts per million of hydrogen sulfide. And this is in the same chamber condition. This was the reference concrete. These are after 4, 8, and 12 months. So similar sort of, this is for gas phase, even higher levels of deterioration. This was with a limestone-based Portland cement system. This was a granite-based, so that's contrary to a lot of the information out there that you'd be using limestone. The bulk of these mixes that have been looked at here are using 80% slag replacement. So this is effectively trying to replicate the old-fashioned supersulfated cements that were used in Europe for acid resistance and have gone out of favour, but they're sort of making a comeback with people just blending their cements. This system also had this was a geopolymer system, which again in this gas phase came up with the lowest numbers, but not vastly better than what was coming up with even the 80% slag requirement. And then there's partial immersion, again showing that it is, generally speaking, a more aggressive environment, primarily because of this the fact that the moisture condition is so important in this aggressive attack. Again, the reference concretes having higher deterioration rates, and these are these 80% slag systems, and this is the geopolymer out here. Calcium aluminate wasn't used in that particular study that time. This was the early phases for a calcium aluminate slag blend, and the numbers, this was just early stuff, but the numbers came out pretty well. This is from many years ago in South Africa. They have a sewer design manual in which they include calcium aluminate and siliceous aggregate. They have estimated rates of corrosion per year, with also with a dolomitic aggregate or with a calcium aluminate based aggregate, which gives very, very low numbers. And so, but it's a useful document because at least it is based on quite considerable survey work and comes up with some indications as to how you can reduce your sacrificial layers with different kinds of use of materials, such as calcium aluminate. Just some other different studies that have been done. This was stuff done with Rockler some years ago. They were used, this is a heat-cured fly ash-based geopolymer concrete, and this was in a sewage chamber over a 3-year period and performing very well. And indeed, there was a sewer line that they had where they had put in pipes with both their standardized Portland cement-based concrete and the geopolymer concrete, and it performed extremely well in that circumstance. And the Thames Tideway, which is a huge project in the UK, which is to be able to deal with both flooding and sewage, and some parts of that have this 80% slag as well. So there are real live projects out there. There are a lot of smaller trial projects that are helping to verify the performance of these kinds of systems, but it does look as though, well, obviously calcium aluminate cement has been in this space and has been almost the benchmark of performance for a long period of time. Geopolymer concretes have great promise. They are a very different chemistry from just a standard hydration product with Portland cement base. And high volume slag concrete seems to be performing pretty well in some of these exposures and is being used. And so I thank you for your time. I hope you find this interesting.